welcome back to the sixth part of our third week, and we're still doing dynamic programming. And where we left off last time was when we said that we want to come up with a DP-based solution to the problem of constructing an optimal binary search tree, where you're basically given keys and frequencies as input. So just to recall the notation, we had a sorted array A of keys, and we also had a frequency array F, which told us how frequently each of these keys would be accessed, and we wanted to build up a BST which had optimal total cost. And I'm just going to be picking up from where we left off last time. So just in case you're coming to this video directly, I would strongly recommend that you watch the previous one, because it's going to be very unlikely that any of this makes sense if you haven't seen the previous video. Okay, so let's continue by thinking about what our subproblems should be. Based on what I hinted at last time, you've probably guessed that our subproblems should involve subarrays in some form. So I want to basically talk about the cost of an optimal BST for the subarray AI to K. Okay, that's going to be my subproblem, or my family of subproblems, right? And once again, let's run through our checklist to see if these subproblems make sense. First of all, where is the answer? Well, again, this is reasonably transparent here. We just set I to 1 and K to N. So then you're looking for an optimal BST in the subarray that starts at 1 and ends at N, but that's essentially the whole array. So we are basically done if we are able to compute the values for all of these subproblems, because in particular one of them holds the answer. And because of that, we should feel very motivated to actually compute the values of these subproblems at this point. Okay, what are some natural base cases? Well, let's say that you're looking at singleton subarrays, for instance, right? Here there is really nothing to do. The BSTs basically have one element and it's at the root. So if I is equal to K, then dp of I comma k is just going to be the frequency of I, because that's just a simple tree with a singleton element. So there's really nothing else to be done here. Now, are there other base cases that you can think of? For example, prefixes or suffixes. So if you fix I equals 1 and let k range over 2, 3, and so on up to n, or maybe fix k at 1 and let I range from 1 to n. Do any of those qualify as interesting base cases? So it turns out that you can think of these as some sort of extended base cases. So let's interpret our recurrence visually as a table here. So this is our left index I, and this is our right index K, and typically we are interested in the entries where K is at least I. So the diagonal entries is what we said would be the natural base cases. So dp of I comma I is equal to f of I is what we have so far. And now you could potentially start off with this first entry here and build up the entries to the right. But that is something that will fall out naturally from the recurrence, so I don't want to do it explicitly as a part of our discussion of the base case. So what's going to happen when you're through with the base case is that the diagonal is going to be fully populated, and then it turns out that for the DP that we will build up, there are multiple ways in which you could choose to fill this table out. So we will come back and talk about that in a moment. But in terms of where we are on the checklist, we have a sense of conviction that this is a good set of subproblems because it holds the answer in a very evident way, and we also have some natural choices for base cases, and we are also motivated by how we saw the cost function being broken up earlier in the previous video. So I think we are hopefully on the right track here. So let's talk about how we can evolve a recursive relationship that will help us compute whatever we have decided to store here. So inspired by what we saw last time, let's say that we're going to begin by making a guess on where this mysterious optimal solution finds its root. And again, we don't really know for sure. This is the subarray that we are currently focused on. And let's say that the root is sitting at some index r that is between I and k, right? Now we are going to examine all possible choices of r, and these are our exhaustive options, and we are going to pick the best, which is just pick up the minimum cost. So this dp in the recurrence is going to turn out to be like a min over choices of r between 1 and k. And well, we know that whatever this r is, okay, if we want to eliminate r from consideration so that we can dive into our base cases, we need to account for how the root contributed to the total cost. But we already know what that is. That is simply the sum of all the frequencies of all the elements here, because like we said, every element has to do like a salam at the root before going further and exploring the BST any deeper. Even if the key was the root itself, we have an access cost of 1 associated with it. So no matter what the choice of the root is, you are going to pay a total cost of the sum of all the frequencies of all the elements in this subarray here, just to account for the root element. But this fully accounts for the root element. So once we have written this down, we can move on. And now we have our recursive subproblems, right? So our subproblems are now going to range from I to r minus 1 and from r plus 1 up to k. These are the two subarrays that we are looking at. So we are going to basically invoke the dp table on these values. So this is going to be dp of I r minus 1 and dp of r plus 1 comma n. So that's basically the total cost associated with making r the root, right? So that's what's going on here, and that's pretty much it. That's actually our recurrence. And if you want to convince yourself that this is indeed the optimum, you can do the two-way argument where we want to say that, well, this cost is achievable. So remember that this is the optimum cost that we were looking at. So we want to say that the cost that we are claiming is in fact achievable. So the optimum is either this or even better, but then we say that, oh, you cannot do better because this is also a lower bound on the optimum. And to say that you can manage with the claimed cost, Well, again, you rely on the induction hypothesis to give you valid BSTs that achieve these costs here for these subarrays, and you take those two BSTs and stick them together with the rth element being the root, this going on the left and that going on the right. So that will be a valid BST, and it will have the claimed cost because of everything that we have discussed so far. So that's why this is a valid upper bound on opt. And why is it a valid lower bound? Well, that's a similar argument as before. Suppose somebody gives you a BST that does better than what you have computed here, then you look at this so-called optimum BST and you ask yourself, well, where did this BST root itself? It must have been at some index R, and that index was something that we looped over as well. So if you manage to do better than us, then that means that something is broken with the induction hypothesis, because this BST must have paid this cost anyway to access the root as we went around accessing all the elements. And on the rest of it, well, for this BST to beat us, it must have done strictly better on at least one of these subtrees, right? But then that would violate our induction hypothesis, and that's basically the sketch of the argument for why this recurrence is actually correct. So now let's just do the rest of the checklist, which is to say that you can actually compute these entries without getting into trouble. So the last thing that I want to talk about a little bit is the order of computation. Remember that it's important to know in what order you're going to calculate the entries of your DP table so that you don't get stuck in cycles, or you're not trying to ping the table for a value that has not yet been computed, and then you might just get stuck forever. So we want to make sure that our dependencies are not cyclic, and the easiest way to see that is to propose a computation order which basically doesn't get stuck. And this has been reasonably obvious in the examples that we have done so far, but here I'd just like to be a little more explicit about it. And in fact, let's work through this with an example. So here's a 6x6 DP table. So this is when n equals 6, and let's say we are focused on the subarray between 2 and 5. So we are trying to calculate the DP table entry that's out here. And let's think about what are all the table entries that we would have to look up to support our calculation, right? So the root could be 2, 3, 4, or 5. And if it's 2, then we will have to look up, well, the left entry is going to be empty, so there's nothing to look up there, but the right entry would be 3, 5. If the root is 3, then the left entry is going to be 2, 2, and the right entry is going to be 4, 5. If the root is 4, then the left entry is going to be 2, 3, and the right entry is going to be 5, 5. And if the root is 5, then the right entry again is non-existent, but on the left we will have to look up 2, 4. So these are all the entries that we would have to look up. So let's just identify them out here in the DP table. So 3, 5 would be here, 2, 2 is here, 4, 5 is here, 2, 3 is here, 5, 5 is here, and 2, 4 is here. And this is a pattern that you may have guessed when you saw the recurrence itself, that when you're trying to compute the DP table entry for I, j, you basically go, you've been using the indices I, k. So let's say you're trying to compute DP I, k, then you basically have to look up values of the form dp of I, r minus 1 and dp of r plus 1, k. So you're basically sticking to your lane in terms of the row or the column, and you're either going further up all the way to k, or you're going further up all the way back to I. So those are the kinds of lookups that you have to do. You're in the same row and the same column, and you're basically moving backwards, and you never have to in some sense, go below the diagonal. So the diagonal is what we said was our base case, if you remember from earlier. And so what happens when you're trying to compute the ijth entry is basically you walk backwards till you hit the diagonals on both sides. That's essentially what's happening. So one natural order of computation would be to say that you can compute diagonal forward. So the base case would be that you compute all the diagonal entries, then you compute all the upper diagonal entries, which is like all the entries that are just sitting above the diagonal. And again, you will not have any trouble with the lookups if that's where your next round is going to be. But if you can also do it row wise or column wise, so you can start from the bottom and work your way upwards. So when you're filling out the bottom row, go from left to right, and that will always ensure that you're never lost, because so all you have to ensure is that when you are at ij, everything to the left of you and everything below you has been already computed, and any execution order that respects that invariant will be a valid execution order for this problem. Okay, so I hope that helped, and this would be a nice challenge to actually implement and try out for yourself. So feel free to attempt that if you would like to. There are pointers to actually some implementation challenges in the course notes. So if you are so inclined and you enjoy programming, it's an entirely optional component, but I would certainly encourage you to try it out if you have the time. In the meantime, it's going to be time for our last problem this week, which is going to be dynamic programming over trees. So that's going to be our last video, which is up next. I will see you there, and thanks as always.